All right, we're going to now do this is now 19.21. We're doing state A. You've got 0.125 mole of diatomic gas starting at 1,000, and we're at 100 kilopascals. So it's a little bit different initial conditions. And then we're going to cool it isobarically to 300 Kelvin. And let's go to what we know first and fill in the chart, and our goal is to draw the PV diagram. So in this case, I've got the initial pressure, right? And then in this case, look at the temperature range and the type of gas. It's diatomic in this temperature range. Boom, let's get let's go over that board really quick. Let's go right into this area. We know the degrees of freedom because we're in this temperature range for the entire problem. And so notice we can get CV and CP. R is 8.314 joules per mole Kelvin. Looks like that just squeaked in. All right, and so we're going to know these numbers. Take a second to punch those in. Let's go fill that in on the chart. And I've got that written here. So just so we said, this is degrees of freedom 5, and this ends up being 20.785. And this one's 29.099. Is that right? I believe when we do this thing, that's what we're going to get. Okay, 8.314 has 4 sig figs. That's why these have 4 sig figs. All right. Do we know the initial volume? No. How do you get it? Pause the video if you want. 3, 2, 1. Ideal gas law. I know P initial, V initial equals nRT initial. So notice V initial is nRT initial over P initial. What do we want to watch out for when we plug in? Temperatures are in Kelvin. Pressure is in pascals, so don't forget the times 10 to the 3. All right, you should get, in this case, what was the volume I got? I'm going to double check here. Ooh, we might have to change these numbers. Let's take a look. Oh, whoops, that's not my calculator. All right, just confirming. So N was 0.125 times R 8.314 times T initial, which is 1,000. Okay, so far everything's got 4 sig figs. Divided by the pressure, 100 E3. So I got 0.01039.3. I think everything had 4 sig figs. 4, 4, 4. And what was the R had 4 as well. Yeah, so, okay, that's interesting. So here I'm going to go, this is going to be 0.005, and this would be 0.010, making sure I didn't screw that up. All right, that seems reasonable. So, while not exactly here, it's pretty darn close to right here. Just barely over here. So that's point A. Right? Basically, almost exactly spot on 0.010 and 100. So there's point A. Great. Now, in this case, what was the next part that we want to figure out? P final and V final. Well, what does isobarically mean? Constant pressure. Good. All right. Who am I talking to? I'm talking to a camera. I'm losing my mind. I've been doing this for weeks, going crazy in here. Whatever. We know the pressure is going to remain the same. Awesome. How can I get the final volume? Let's do our ratio trick again. You could say, oh, can't I just use this? Now I know NR. You could. I guess you could plug it in right there. I like to show the ratio trick because sometimes we don't know the number of moles in the problem, but you could still figure this out even without the number of moles if you have these pieces of information using the ratio. So I recommend learning the ratio trick. P initial, V initial equals NR T initial, P final, V final equals NR T final. The N is not changing. We're assuming we do not have a leaky system. That's why I didn't need subscript. R. What was constant this time? Pressure. That cancels. So now I can get V final is equal to all right. Now in this case, what was T final? That one's 300. This is 1,000. All right. And V initial was this junk. Cranking that out, what do we get? So times 0.3. There's our 0.311 back again. Whoops. 0.003118. This one only has 3 sig figs. Right, we had 4. Okay, got it. Now we can draw that one. Where is that going to be? Just a smidge over 0.003. Oh, shoot. These increment sizes look whack. All right, let's try to split this up. So 1, 2, 3, 4, 1, 2, 3, 4. So now the increment size will make a little bit more sense. So this is 0.001, 0.002, 0.003, and it's just above that. Also at 100 kilopascals. So that's B. All right, we can draw our process now if we need to. Think, we have to include the arrow. All right, Q in. How do I get Q in? You can pause the video if you want. 3, 2, 1. NCP delta T. This is a constant pressure process. We do not use CV. We use CP for constant pressure. All right. And now in this case, what's our N? 0.1250 times CP, which was some screwball number, 29.099, times delta T. What is delta T? Negative 700 3 sig fig Kelvin. We're going from 1,000 down to 300. T final is 300 minus T initial 1,000 gives negative 700. So times negative 700. So I got negative 2546. I love to track the sig figs on these because at the end, we're going to check if the first law is valid, and it's only valid to the column of sig fig, right? So nothing's ever going to perfectly match up when we do these problems. So you have to kind of track the sig figs to know if you did it right. All right. You don't have to be psycho about it, but just keep a couple extra laying around once in a while. All right. What's next? Work done by. I guess, let's just do it. Pause the video if you want to try it yourself. Here I go. The general condition, work done by, is equal to the integral of P dV. Now, if P is a constant, that factors out. That would just be P times the integral of dV, which is just P times delta V. Be careful. Think, is delta V positive or negative? It's shrinking. The volume gets smaller. We're going to have about negative 0.07 or something, 0.007. So I'm going to punch this in. You can see what you get. So the pressure is 100. Oh, we've got to watch out here too. Don't forget the pressure's in kilopascals. So it's 100 times 10 to the third pascals, and delta V is some negative number. It's the subtraction. This minus that negative. So 100 E3 times 0.003118 minus 0.010393. And what did I get? Negative 727.5. So 3 sig figs too. All right. So another way you could get that, just get the area under here, right? So if everything happened to line up on the grid lines exactly, I would use that. But because these aren't exactly lined up on the grid lines, I would recommend doing it this way, all right? Otherwise, you're going to introduce significant errors and you might get frustrated thinking something's not true. All right. Now, delta E internal, I want to get that in two ways. Shortcut, delta E internal equals N CV delta T, always. So let's punch that in and then we'll check it with the first law. So we're going to try the shortcut. So 0.125 times CV, which is 20.785, times delta T. Delta T is negative 700. Negative 700. So I got negative 18.7. That probably sounds familiar. All right, and then just check it. This should be a 3 sig fig number. Now, we could check first law. Either one of these methods is great. Shortcut, that wasn't too bad. First law, here's how we could use the first law. Delta E internal should equal Q in minus work by. So this should be negative 2546 off in the tens column minus negative 727.5 off in the ones column. So our result should only be good to the tens column when we do the subtraction, right? The worst column. So negative 2546 plus, because minus and negative is plus, 727.5, and I get negative 1818.5. Are these different? No. This is why I'm saying it's kind of useful to track the sig figs and why you see me kind of going nutso over here with extra sig figs. What happens is in certain processes you'll get a subtraction of two numbers and lose some sig figs here. And so basically we expect the first law and this result to match up only to the crappier column of sig figs, and they do. Let's do some reality check. That's always good here. Okay, we've done a bunch of the math, we've seen this. Let's think about it. In particular, the minus signs. Let's check those minus signs. I want you to get in that habit. Look, what are we doing here? We're compressing the gas. The volume is getting smaller. We're crushing the gas. This is a system like this. Oops. Right? And we're compressing it like that. Whoa, that's kind of funny. Whoops, oh geez, I'm dropping stuff everywhere. Where are we here? All right, so in that case, if we're compressing it, I had to do work on the gas to compress it, right? I squeezed it down. So in that case, the gas is doing negative work, right? Its volume is being shrunken. It's trying to expand the gas, but failing. It's doing negative work. Process goes to the left. This matches up with what we see over here on board 2. Right? When the volume goes up, typically delta V is greater than 0 and work done by is greater than 0. If the volume goes down, we expect these signs to flip. Delta V would be negative, work done by is negative. Right? And then let's think. It's being cooled. Is the sign on Q reasonable? Yeah, if you're cooling something, you're inputting negative heat. So we've seen an example where you heat, in the last problem, we added heat, we increased the temperature of something, we added positive heat, right? And the pressure went up. In this one, we kept the pressure constant, but we cool it off, so the volume had to shrink. That's the same thing like putting well, here's the process, literally right here. Let's just look at it and then be done. Just holding it up while I seal it. Okay. Right? When I put this in here, the pressure is constant and the volume goes down a little bit. It's that simple. That's it. All right, next video.